examination. So that is generally you guys underperformed in. Now, may I remind you, if this is a question that you didn't underperform in, then please do endeavour to forward it on to a question that is more appropriate for you. But for now, we're going to start with the question that you see on the left, and that is about George and Eva, because George and Eva have nothing better to talk about other than the pondweed in their fish tank. I would recommend getting a different hobby, but let's just focus on their conversation. Okay, so if we start with George to start off with, if we shine a light at pondweed, we can tell how fast it is photosynthesizing. All we have to do is measure the change in oxygen level in the water. So he's relating photosynthesis to the oxygen level in the water. Eva, the little heathen, turns around and says, I don't think that can be right. You know this is going to kick off. I think we need to know what happens to the oxygen level in the dark as well as the light. All right, okay. So joking aside, it's an interesting question. It's an interesting discussion actually when you look at the science behind it, because we're talking about the comparison between this clear bottle and the pondweed inside it and the oxygen level in the water, and we're talking about the black bottle, which is obviously not letting any light in. So immediately as a student, I would have gone, okay, well that must mean that if there's no sunlight, that there's probably not going to be a lot of photosynthesis going on in there. So something else must be going on, and that something else is respiration. It's important to understand that photosynthesis and respiration usually happen at the same time, but the rates of each of them differ depending on the light level that each pondweed is exposed to. So if there's more light, there's more photosynthesis than respiration, and if there's hardly any light, then obviously respiration rates will be much, much higher. All right, okay. They set up an experiment to test their ideas. To do this, they used a black bottle and a clear bottle. Into each bottle, they put the same amount of water and pondweed. That's important, obviously, for a valid experiment, otherwise known as a fair test. It's also a control variable, so that is something, that's a terminology that, of course, you should know from your own control assessments. They measure the oxygen content of the water, and they put bottles right next to a light. After a week, they measured the oxygen content of the water again in each bottle. Right, let's have a look here. Okay, so here are their results. Oxygen in the water before the experiment, so the natural oxygen level before the experiment was 8 milligrams per litre. Oxygen in the black bottle after a week went down to 5 milligrams per litre, and oxygen level in the clear bottle went up to 10 milligrams per litre. So this went down to 5, this went up to 10. Now let's look at the question. Explain the results of the experiment by analysing the data, and remember what I taught you before, put a slash across the and. Use this to explain why Eva is correct. Right, explain the results of the experiment by analysing the data. Right, let's do that one first. All right, you want top marks, you're going to do as I would advise. So let's have a look here. Right, okay, so if we're looking at the clear bottle to start off with, let's look at how to get the top marks. So the clear bottle, it went up to 10 milligrams from originally 8 milligrams. So I would recommend that the first thing that you guys should do is think, okay, well, photosynthesis is occurring a lot more here because light is allowed to pass through. Okay, now because light is allowed to pass through here, you should remember the formula for photosynthesis is, okay, well, now try and think, what is the formula for photosynthesis? You get carbon dioxide from the air, you combine it with water that came from the roots, and that makes glucose and oxygen. And in fact, if we're looking at this logically, how much oxygen was produced in this case? Okay, you can see a differential of 2 milligrams here. Okay, there's a differential of 2 milligrams here with the light content clear bottle, the light exposed clear bottle. So that's a quantitative analysis. Then you look at the black bottle over here, and you can see that the black bottle actually went down from 8 to 5 milligrams, which is a difference of 3 milligrams. Okay, so let's have a look at what the mark scheme says. Here we go. Photosynthesis is faster than respiration, so oxygen increases. That is for sure the case here. In the clear bottle, photosynthesis produces 2 milligrams more oxygen than respiration uses up. True. Okay. In the dark, respiration uses up 3 milligrams of oxygen. Yeah, we know it went down from 8 to 5, so it uses up 3 milligrams of oxygen. Now, if we look at the difference between +2 and the difference between -3, so the difference between +2 and -3, ladies and gentlemen, is 5 milligrams of oxygen. Therefore, photosynthesis makes 5 milligrams of oxygen. Okay? That is how you are going to be able to answer this question to get tip-top marks. Look at what they are saying here. Answer includes an appreciation that photosynthesis and respirations are happening in light, but that photosynthesis is faster, so there is a net oxygen increase. Remember what I said at the beginning? I said both of them are occurring at the same time, but the rates are different depending on the amount of light exposure. And only respiration occurs in the dark using up oxygen, and this is coupled to a quantitative analysis. That means you've got to use the numbers of the results. So have we done that? Yes, we have. Did we look at these numbers? Yes, we did. Did we figure out that there was a difference of 5 milligrams, the difference between +2 and -3, +2 and -3, and that difference is 5 milligrams, and therefore we can conclude that 5 milligrams of oxygen is produced by photosynthesis. Okay. This one here, very, very simple. As well as light, plants also need magnesium for photosynthesis. Why plants need magnesium? Magnesium makes chlorophyll, ladies and gentlemen, the green stuff in plants, and therefore chlorophyll is needed for photosynthesis. Okay, right. So that was question number 3. Now, the other one that you underperformed in is question number 7. And question number 7 also, before I go to question 7, let's go to question 6. This is another big one that you guys underperformed in, and it's one that traditionally loads of children underperform in. Now, on the YouTube channel, there is a very key video on how to draw covalent bonded structures. So I would strongly recommend that you also have a look on that video for clarity. But for now, what I've done is I've got 2 diagrams that I'll show you in a minute. Let's have a read of the question. Question 6. Calcium reacts with oxygen to make calcium oxide. There's the formula. Calcium plus oxygen equals calcium oxide. Calcium oxide contains the ions Ca2 plus and O2 minus. Okay, straight away, my brain would go, right, okay, that's a 2 plus. That's in perfect ratio to a 2 minus. So that's why you need one of them for one of them. That's what the formula is, calcium oxide. All right. Use the formulas given to write a balanced simple equation for the reaction between calcium and oxygen, and use the dot and cross model to explain the bonding in both oxygen, in an oxygen molecule, and calcium oxide. You only need to draw the outer electron shells. Right, as I said, if you want a key diagram to help you, I would strongly recommend you have a look at the covalent bonding video on YouTube. Can I also, let's just focus on first and foremost the bonding between calcium and oxygen. This is what I would do as a student. All right, so it contains the ions calcium and oxygen, and you know that calcium, which is on the left hand side of the periodic table, is a metal, and you know that oxygen is a non-metal. So metals combining with non-metals are ionically bonded substances, and the formula for which is going to be CaO. They're asking you to draw the dot and cross models for calcium oxide. So let's just do that. Okay. So if I bring up a dot and cross diagram for you, can I just point out a couple of things? This is how you do it. First of all, find out where it is in the periodic table. Okay, it's in group 2. And when you look at the electronic structure, it's got 2 in the first shell, 8 in the next, 8 in the next, and 2 in the last shell. Okay? Is it easier for calcium to lose 2 to get a full shell beneath it? Or is it easier to gain 6 to make a full outer shell of 8 in the outer shell? Now, obviously, it's going to lose 2, and that's why because you've lost 2 negative electrons, you become positive. In fact, you become 2 plus or positive 2, right? Now, because you've become a 2 plus, there's a positive charge on your ion there. Now, let's have a look at oxygen. When you're looking at oxygen, ladies and gentlemen, oxygen originally, this is a bad diagram here because that's not quite right, but I'm going to go with that. If you looked over here, you can see oxygen originally is 2, 6. It's got 2 in the first shell, 6 in the next shell. Now, if you understand what I just did with calcium down here, you'll know that oxygen, it's easier for oxygen to gain 2 electrons than to lose 6 to get a full shell inside. Okay, so what we're going to do, we're going to gain 2, and when we gain 2, ladies and gentlemen, oxygen becomes a 2 minus charge, because if you gain 2 negatives, you become negative. Now that's a negative, that's a positive, and as a result of that, they will be attracted to each other electrostatically, and that's why they bond, forming a strong ionic bond. Okay, so just to clarify one more time, remember it's easier to lose 2 electrons, so those 2 electrons jump over to oxygen over here, which had 6 originally. Now he's got 8. Because he's got 8 in his outer shell, that becomes a 2 minus charge because you got 2 more than you had to start off with, and that became a plus 2 charge because you lost 2 electrons to start off with. Okay, and that's an ionic bond. So that is how you would draw calcium. Remember, you're only drawing the outer electron shells, and over here you're only drawing the outer electron shells here as well. Remember, this diagram's a little misleading, ladies and gentlemen, because they've just drawn all dots here. Ideally, what you should be doing is you should be drawing a dot and cross diagram showing the outer electron shells being 0 here, because remember, you lost those 2 outer electrons. And over here, there's the 2 outer electrons, the crosses that came from the calcium are represented by crosses, and the dots, which was 6 to start off with, are representing the electrons that belong to oxygen originally. Okay. It's tough, it's tricky, I get that, but hopefully that should clarify things a little bit more. All right, so I'm on the wrong one. Okay, so oxygen was the other part of the question. So oxygen, remember what I said to you before, I always work out the electronic configuration of the atoms first. Oxygen is in group 6, okay? It has a proton number of 8, and therefore it's got an electron number of 8 as well. 2 always go in the first shell, 6 go in the next shell. That means that he's got space for 2 more electrons, because remember, all atoms like to have a stable octet, which means they all like to have 8 electrons in the outer shell. You can see he's only got 6. You can see that this oxygen, and so therefore he wants 2 more, sorry. And here, he's also only got 6, and therefore he wants 2 more as well. And so what's the logical thing for them to do? It's to share these 2 in the middle here, and that's exactly what they do. That's why it exists as O2. Now, let's count up the outer electron shells. 1, 2, 3, 4, 5, 6, 7, 8. And then this one also, just to tell you now, is also sharing 2 pairs of electrons in the middle, so it's a double bond, but it's got 8 electrons all together as well because of the 2 pairs that are being shared in the middle. That's a double covalent bond, and that's how oxygen attaches to itself. That's why it's existing as a O2 molecule. All right. That's tricky. That's tough. Don't get me wrong. You're going to find that tricky and tough. I understand that, and I really get that. So if you need further clarity, please endeavour to ask your teacher about this. There are, as I said, I've already put a video on YouTube about covalent bonding, and I'll try and make one for you for the ionic bonding one as well. Okay, so question 6 done. That's all to do with ionic and covalent. We're going to move on to question 7 now. Okie dokie, question number 7. Phil and Kate analyze the solution. Look at table 7. It shows the test that they use and the results that they get. So test number 1, 2, 3, 4, 5. Test on solution, the appearance. Test 1 is normal appearance. Test 2 is the flame test. Test 3 is adding sodium hydroxide. Test 4 is adding barium chloride. And test 5 is adding silver nitrate. Okay, right. Kate concludes that the solution is potassium iodide. Potassium, straight away, is a metal. You should know that with the flame test, potassium will give you a lilac flame. Okay, if you don't know that, have a look at your flame test colors in your revision guide. For example, calcium will be red, sodium will be orange, potassium, as I said, is lilac, etc., etc. So you need to know those key flame test colors. Okay. She knows it's potassium straight away because it gives a lilac flame. Iodide, which is a halogen, can only be really tested with the use of adding silver nitrate. Now, when you add silver nitrate to this solution, a precipitate is formed. Now, what is a precipitate? Remember, a precipitate is where a solid forms, an insoluble solid, I should say, forms in the presence, in a solution, basically. Now, what does that even mean? Right, what I've got for you here is a bit of a summary for you. Okay, have a look here. So when you add silver nitrate, when you're testing for chlorides, bromides, or iodides, chlorides will give you a white precipitate, bromides give you a cream precipitate, and iodine gives you a yellow precipitate. And so this is how this gentleman or lady know, because it gave a yellow precipitate, which means that it was an iodide compound. And so that's how you can conclude that this was potassium iodide. Okay, now moving it on to flame test. Flame test, this is important. How do you do a flame test? Well, the first thing you need to do is get a little loop of wire. In fact, what I'll do is I will show you the particular page that pertains to this. Okay, if I go to page 156 in the additional science books. Okay, so these are the flame tests. This is what you do. Remember, ladies and gentlemen, the first thing you absolutely must do for this is you need to get your flame test wire. Okay, there it is. There's your flame test wire. Okay, there it is. You need to dip it into some hydrochloric acid. Okay, you dip it into some hydrochloric acid. The next thing you do, you then dip it into the substance that you want to test, so that the solid substance gets stuck on this loop here. Okay, and then what you do is you gently place the whole loop into the flame, which is a roaring blue flame, and whatever color comes off it will identify what substance is in it. Okay, so you can see here, look, lithium red, sodium yellow, potassium lilac. That's how you do it. Simple as that. And that is how you do your flame test. All right, ladies and gentlemen, next one. Okay. Right, question number 13 is the one we're going to move to now, which is to do with carbon dating and nuclear equations. Okay, bit of a tricky one, this one. Carbon-14 is a radioactive isotope which decays by emitting a beta particle, right? There it is. There's the beta. It's come off. So an isotope of nitrogen is formed, as shown in the nuclear equation below. Straight away, isotope of nitrogen, Mr. Sony would go, okay, what's the mass number for nitrogen? What's the proton number for nitrogen? Okay, straight away, I have a look at... let me set this up for you. I have a look, and by the way, this is always for you to you can pause the video and really analyze this a lot further. What I'm doing is I'm talking through it so that you can marry what I say with this over here. Okay, so you can use both, of course. So going back to what I was saying, let's look at this. Nitrogen has a mass of 14 and a proton number of 7. That's very easy to find out from your periodic table, guys. Very, very easy to do. Now, if you did that, and you can see that originally the mass of carbon was 14 and the proton number of carbon was 6. If you look at the periodic table, as I said to you before, it's still got a mass of 14, but a proton number of 7. So, what's happened? What's happened here? Let's look at this. The mass hasn't changed, but the proton number went up by 1. That means that one of these neutrons in here turned into a proton. That's what happened. One of the neutrons here turned into a proton. And when that happens, a beta particle is emitted. Remember, beta has a -1 charge. Okay? And a mass pretty much of 0. That's why it's represented by 0 and a -1. Okay, so that, in summary, honestly, that is a major part to you getting most of your marks. Complete the nuclear equation and describe in detail what happens to the particles in the nucleus of the carbon atom. So, include ideas about mass, atomic number, and a description of the emitted beta particle in your answer. So everything I've already said to you tells you about what happened to the mass number, that it stayed the same, what happened to the atomic number, it went up by 1, and this means that the neutron in the nucleus turned into a proton, which is why the number went from 6 to 7. And finally, the thing that I haven't said is, what's the description of the emitted beta particle in your answer? Beta is a high energy electron. Simple. That's how you get your 6 marks. If you want a summary of what I've just said, it's just here. Okay? And finally, question number 14. Okay, question number 14. This question is about nuclear radiation. Radioactive materials decay naturally. The half-life is a measure of how quickly the radioactive materials decay. Look at the data below about the activity of 4 radioactive isotopes. You've got isotope A, B, C, and D. And you can see the count rate goes all the way from 6,000 down to 0. So, which isotope is, sorry, I don't know what I'm doing now, I'm slurring away. Which isotope has the shortest half-life? 2 ways you can do this. The way I would recommend highly, there's your start half-life. So there's your start reading, which is 6,000. Half of 6,000 is 3,000. Read it across. Boom. Read it down. Boom. So isotope A has a half-life of roughly around about 20 seconds. Isotope B, sorry guys, my mouse is just a pain, is roughly around about 45 seconds. Half-life of C is nearly 64, 65 counts per minute. And half-life of, well, D doesn't even get there. It's just trailing behind, dribbling away in the background. So the short answer is the shortest half-life is A. And the explanation of the answer is very, very, very simply that the count rate goes down to 3,000 in 20 seconds. Right? Simple as that. Very, very simple. Okay? You should also be saying what half-life is, and half-life is the time taken, sorry, this mouse is playing up, guys, is the time taken to go from from the full count number down to half its original value. Okay, it's the time taken for half the original number of atoms or nuclei to decay. Okay. Radioactive carbon 14 has a half-life of 730 years. Carbon 14 can be used to find out the age of some materials. Explain how. This is for 2 marks. All right. Very important. Remember, carbon-14, okay, carbon-14 over here is detectable at the same level in living organisms. It basically remains constant in organisms, all right? When we die, that reduces, okay? And it's how much of a reduction that will determine the age of the organism, all right? That is your answer. If you want a really definitive one, it tells you down here. And finally, wooden beams from a house are thought to be from trees cut down about 100 years ago. The radiocarbon dating method cannot be used to show that 100 years is the accurate value. Suggest why? Well, look at it logically. It's got a half-life of 5,730 years, and we're trying to date something that is only 100 years old. There's hardly going to be any reduction in count rate over the last 100 years. That's why it won't be suitable. Okay. That, ladies and gentlemen, is a whistle-stop tour of your particular exam paper, B4, C4, P4. I hope you found that useful, and please endeavour to pause and watch these videos as much as possible, because ultimately this is for your benefit. So I hope you found that useful. Take care, folks. Thank you. Bye-bye.